Okay, so today we're going to look at calculating and reporting effect sizes, and we're going to talk about when they're required and why we should be using them, and how we interpret the effect size when we do actually calculate it. So I might start with a couple of quotes from two researchers who are instrumental in actually bringing about effect sizes, Glass and Cohen. And you're probably mostly familiar with Cohen, who did a lot of work in effect sizes, and in fact his interpretation, although with caution, he states, is what most people tend to use. And I've tried to, throughout the presentation, give you references where you can actually go and read up a little bit more about the sorts of things and the rationale behind how effect sizes came about and how you apply them and use them effectively. So what are effect sizes? They're basically a measurement of size or magnitude of an effect. So they're there to help us have information about the size of the effect that we're actually trying to measure or determine. It tends to be independent of sample size. It's meant to be a standardized metric, and it also can be considered a strength of association. So why are effect sizes important? Why do we need to look at reporting effect sizes? In some fields that's done more than in other fields. So for instance, in biomechanics, we tend to have effect sizes are reported as standard, whereas in some medical areas, we might not necessarily report effect sizes. So it tends to be field dependent about whether they're reported or not. But the importance of effect sizes is it allows us to communicate what the practical importance of a result is. So if you've been to some of my other presentations, you would have known that I've always talked about representing statistical results with respect to clinical importance. And an effect size is really about helping to communicate the practical importance of the result, or giving a quantitative measure towards what is clinically important. So an effect size will help you uncover something that maybe is really important but didn't reach statistical significance, and that might be because it was underpowered, new field, or you didn't have enough of the clinical population to be powered to detect a difference. But it also indicates where you might have an unimportant result even though you've reached statistical significance. Okay, and that's probably a really important thing. That is particularly relevant if you have very, very large sample sizes. So the larger your sample size, the more likely you are to find a significant difference by chance than you are if you've got smaller sample sizes. So an effect size inherently is about providing information about how important is that difference or that association that you've detected. It can also be used for meta-analysis, and I'm not going to talk about that at length today during this session, but it is used in meta-analyses. It can be used for calculating power calculations a priori. Some people use the effect size, and you would have seen that the information that we use to calculate the effect size today is actually the information that we often put in our power calculations when we're doing power calculations. So there's obviously a very strong relationship between the two. More and more journals are requiring effect sizes to be reported. So often you will now get a reviewer who says, that's great, can you add effect sizes to table 2? Or, can you give us some information about the effect of those differences that you've detected? Importantly, for many of us in the health area where we use the American Psychological Association's guide for referencing and formatting, this is actually recommended as a requirement so that readers can appreciate the magnitude of importance. So from an APA style perspective, this is something that they suggest is essential to any reporting that we do. And they also suggest that we should be using confidence intervals, and there are a few calculators around that allow us to also calculate confidence intervals for effect sizes, one of which I give you information later on today. However, the general principle, according to APA, is that you just need to provide enough information to be able to assess the magnitude of the observed effect. So really it's looking at, is it clinically important? Is what the author's telling me, justified? They're not, skewing the truth. So it allows them to make a critical assessment of the information being presented and to determine what impact that has on whatever the research question was in the first place. So measuring effect size. It can be calculated in lots of different ways, and it depends on the outcomes or the studies that you're doing. But I'm going to focus on the two main approaches. One is the standardized difference between two means, and that's often what you will see tabulated. You'll have means and standard deviations of different groups. And the common ones you'll see are Cohen's D, Hedges D, Glass's delta, and common language effect size. The other approach is to use the strength of association, which is correlation. So those of you who have been in my correlation presentation will know it's related to the correlation coefficient, and you can have some information about the measure of effect based on that correlation coefficient. So just going back to the standardized difference between two means, it is represented, or Cohen's D, as I've been saying, is the D family. So it's a group of standardized differences. And it's the difference between the observations divided by the standard deviation. So we're looking at standard deviation units of effect. Whereas the strength of association, as I mentioned previously, is really based on correlation, so the R family. And it's looking at proportions of variance that is explained by the groups. So we're looking at the R squared and the percentage variance explained, which we cover when we talk about correlation. So now I'm going to present to you some of the different ways of measuring effect size and formulas. Now the formulas are not there to scare you, so please don't be afraid. They're there really just to demonstrate how the means and standard deviations are used for each of the particular formulas to actually calculate effect size. So they're for demonstration purposes, not for you to have to worry too much about the actual formula itself. So as I said, Cohen's D is a standardized mean difference of effect. The scales can be, the variables can be measured on different scales or different measurements. But something that's worth noting is that the Cohen's D is actually an uncorrected effect size. So it's based on a sample and it might not necessarily be a true estimate of the population effect, particularly if your sample size is less than 20. So if you look at the formula that I've provided you on this screen, you can see it's the mean of the first group minus the mean of the second group, and then it's the sample size of the first group and the sample size of the second group, and standard deviations likewise, that are embedded in the formulation for Cohen's D. You can also calculate Cohen's D using a t-test statistic. So if you calculate a t-test, which is basically using your means and standard deviations and sample size, you'll get a t-statistic and a p-value. You can actually use that t-statistic in the formula and calculate a Cohen's D as well. And that's represented by the formula on your screen at the moment. So I talked just briefly there about a bias in the Cohen's D. So what does that actually mean? It means that it's based on sample averages. So, and they may overestimate what's actually in a population effect. So there are ways and means around that. For Cohen's D, it's called Hedges G, which is a correction for bias. So you might find that a Hedges G might be more appropriate. And eta squared, which we haven't covered yet, is corrected for bias using omega squared. So they're two ways in which the bias can be corrected for. And it depends really on your target journal or your target audience, which one is the most appropriate one to report. Later on, I will talk about interpreting effect size relative to what's published in the literature. So even though you might think Hedges G might be the best way to actually report, if everyone in your field actually reports the Cohen D, then obviously for comparison purposes, it would be advantageous to report the Cohen's D yourself. So because then you can compare between studies. Just to look at what the Hedges D is, with respect to the Cohen's d, you can see it's just a numerical adjustment for the Cohen's d, and is seen to be an unbiased estimate of the population of the effect size. Glasses delta is another version of effect size, and it's used when the standard deviations differ substantially between your two groups or conditions. So often you'll find if you're comparing two groups, the standard deviations are very similar, but in some situations, those standard deviations might be significantly different, or it might be, you know, a pre and post measurement. And what they actually recommend is that you choose one of those standard deviations in the formula, and the way to choose that one is to actually determine which one represents the effect of interest. Okay, and the way you would determine that, I guess, depends on your field of study and also depends on what's been done previously. So you will often find that for these sorts of things, someone has already set a precedent within your field and provided a clear rationale about why that choice was made. Sometimes you might need to get statistical advice to support the decision of which way you're going to go as well. Another one that I've used is the common language effect size. It's noted as a non-parametric effect size and is based on the probability of a Z-score. And it basically converts Cohen D into a percentage expressed as a probability. And what it's trying to say is that someone randomly selected from one group is going to be different to someone randomly selected from the other group. And it compares those sorts of things. The actual formula is quite complex, and most authors actually just provide you a link to a spreadsheet to how to calculate it. And as I will show you later, I mean, for most effect sizes, there's a particular website that I recommend you use. You can automate that by using the formulas in an Excel spreadsheet if you've got lots to calculate, but often we've only got a handful to calculate and we use a particular website. My endeavour is actually at some stage to create our own Excel spreadsheet that we can obviously share with students and staff, and they can just have that as a permanent link to, but that hasn't been completed yet, so somewhere down the track. There might also be sometimes when you do a comparison in one sample, or if there's correlated or repeated measures, and then there's a slightly different formula used to calculate. It's still called Cohen's d. It's denoted by a Z instead of the S that we saw before. And it looks at using standardised mean differences for winning subjects designs. Again, you can see with both formulas that you can use either the actual raw scores, or you can actually use the t-test score statistic that you would get based on doing a t-test. But again, there's just a slight difference. The main thing to remember is this is determined based on a mean difference. So they're just a quick overview of obviously lots of different ways of calculating effect size and the rationale between why we would choose certain ones. We've talked about Cohen's d in length, but how do we interpret the values that we would get for Cohen's d? Now, the values for Cohen's d go above 1, but anything above 0.8 is considered a large effect, and then we have medium and small cutoffs determined there, which are pretty standardised across the literature. Some authors have actually further described what they mean, and I've got some examples of that at the end of the lecture today. But I think the most important thing to note is that these cutoffs, and Cohen himself states it very explicitly, are arbitrary, and the best way is to relate the results to other effects reported in the literature, but also to determine in cohesion with the clinical importance. So the effect that you're actually measuring, if it's a difference between two groups, you have obviously the statistical test results. We recommend the effect sizes also be reported, but that all has to be considered with respect to the clinical relevance and importance. So just because you've got a significant p-value and a medium effect, does it actually mean anything clinically? Is that really important? again, that's what I'm talking about. What is the clinical importance of the result? So I think hopefully if you've been to a few of my lectures, what you're gathering now is that it's the overall encompassing picture and story that you're telling rather than relying on one particular statistical result or outcome. So it's about building an argument and demonstrating a story linked together with various bits of evidence to support your claims. So I just wanted to provide you some examples of how you would write that up in results. And so this is an independent t-test example. An independent t-test did not report a significant difference between lower exam scores for males compared to females, although a medium to large effect was found. Now that medium to large terminology is derived from that 0.53 to 0.86. Okay, and you'll see that the effect size reported there is 0.73. Now, one caveat to all these examples I provide in text, the numbers are completely random, well not random, they're completely fictitious because I've derived them to try and tell or provide an example of the story that I'm trying to tell. So sometimes you'll look at that t-value and go, does that actually correspond to that effect size? But I'm just trying to show you how you might report when you have a non-significant result but actually a medium to large effect size. Okay. Let's now look at when we have, so up until now we've really talked about two groups in comparisons. Let's now look at whether when we have three or more groups, we can use eta squared and partial eta squared. Now these outcomes, certainly in SPSS, can be requested in your output, so you can get these directly reported. You don't need to go to an online calculator to have these values presented. So the eta and partial eta squared give you a degree of association for the sample, and then we have omega squared and intra-class correlation, which is a degree of association for a population. So that's just generically speaking. But these values can all be derived through your SPSS output when you're asking it to do some calculations for you. Again, how do we interpret these particular effect size? So for eta squares, they're slightly different values. Small, medium and large according to Palant are presented here as cutoffs. Again, remember these are arbitrary and you need to look at it with respect to the literature and whether it's clinically important. So you'll see that caveat on all of these interpretation slides because that's something that you need to ensure that you recall and remember. Let's have a look at a dependent t-test result. So this is a pre-post type of example. A dependent t-test reported a significant increase in 3K time trial from pre-season to mid-season with a large effect. So you can see we're presenting the mean, standard deviations, the actual t-test result, and then the effect size. If we have a look at an ANOVA result, this is where we're looking at school types. For this example, group differences examined using ANOVA found independent schools had significantly higher IHR scores compared to Catholic schools who are higher than public schools. So in this example, I've shown you that there's a significant effect between groups. I've suggested who are higher and who are lower. But then I've got this caveat statement. Despite reaching statistical significance, the actual mean difference between school types was quite small, and that's based on an effect size. So here you can see that the differences are actually statistically significant, but the effect size is small. So that's another possible scenario that you might have. For chi-squares, there's some other effect size measurements that you can have. So phi is used for a 2x2 chi-square analysis. It's related to the correlation in Cohen's D and is interpreted similar to the Pearson's R or R squared. And then if we have a 3x2 or more categories, then we can look at the Kramer's phi effect size instead. The issue with the Kramer's effect size measure is that it can become biased with increasing number of cells, so that the more cells you have in your contingency table, then the increased bias that you might have in your effect size measurement. Again, interpreting effect sizes, these are based on Palant. And you can see I've given you some measures, phi for small, medium, large, and you'll note that's very similar to correlation. But on the right-hand side, you will see for interpreting Kramer's V that they actually change depending on how many categories are in your contingency table. And they're the guidelines that Pallant uses as an example. Again, these are arbitrary. They need to be evaluated in the context of your results. Are they clinically important and are they relevant? And here's an example, apologies, that's my dog. A chi-square group difference between sex and employment status indicated a significant association of medium effect. And then you see the chi-square result presented and the effect size reported. And then I go further to explain where those differences might lie. So just providing a bit more information. So again, that's how you would embed an effect size within the reporting of the results. So how do I calculate these effect sizes? So I've given you some formulas and told you not to worry about formulas and what to do with those. So this particular website that I've provided, I think provides a really good comprehensive guide to a number of different types of effect sizes based on your study design and the questions you're answered and the sample size. So this is the one that I tend to use quite often, but there are lots of different online calculators for a sex effect size. The important thing really is to make sure you're using the right one based on your study design. What I wanted just to give you is just a couple of examples, 2 examples in fact, of published papers that use effect size. So this is from an academic here at Notre Dame who looked at small-sided games. And you can see here in the example that what he's done is he's embedded the effect size in the text of his manuscript alongside the p-values. So he's reported the p-values and the effect sizes together so an interpretation can be made as you go through. So that's one way that can be used to report effect sizes. The other way is within a table. So this is again from this is from a PhD student here at Notre Dame, and this is looking at effect sizes for between group effects. And you'll note here in this example that not only has this person reported the effect sizes, but they've also reported some terminology that's commonly used with effect sizes, trivial, small, moderate, large, very large, okay? And again, that terminology changes based on who you're referencing for the interpretation of effect sizes. I would suggest that you use the cutoffs and terminology relevant to your field of study. That's probably the safest way, or your journal's requirements. Otherwise reference, and I've got a couple of example tables coming up now on the different ways that you can use terminology to help describe your effect sizes. But I find the small, medium, large is the most common used, and then this is obviously a more detailed option. Some cautions. There's always cautions. There's nothing black and white in statistics. So you need to remember, and I think hopefully I've reiterated it so that you're bored with me saying it, that they're arbitrary and the best way is to relate the results to the literature. Again, so looking at the context of the findings, you need to be aware that effect sizes are sensitive to spurious influences. So standard deviation, obviously from the formulas you would have seen, is a large component. So if you've got large standard deviations, they're going to have a significant effect. You can use pooled standard deviations. This is certainly what's done in meta-analyses. There are corrections for bias. Is it something that you need to consider in the way you report things? Is the data normally distributed? If not, maybe you need to look at a non-parametric option for effect sizes. And also the reliability of the measurement. And the reliability, again, comes back to the variability of measures, and that will have an effect. You need to also have some care when comparing effect sizes of outcomes. So are they comparable? Is it justified to compare them? And the other thing, which is probably a little confusing, is that effect size can imply causality. but it doesn't necessarily mean that your study design had an effect. So when you're using effect size to describe your results, you need to really just be careful that you don't imply causality by the way you phrase your sentences when you're trying to report effect size. So just be careful with the language there as a note. Sometimes the effect size is actually indicating that an effect occurred. So, you know, if you've got a pre-post intervention style study, then obviously, you know, your intervention probably does have a large effect on the outcome measure. But if it's not that style of design, then you just need to be a little bit more careful about how you word your effect size in your terminology. So, in summary, effect sizes help you communicate the practical importance of the result. So the two main areas are obviously an important result but didn't reach statistical significance, or you might have something that's unimportant but did reach statistical significance. So being able to validate why something that is statistically significant actually might not be that clinically important.